Let's say you're building a social media app. In the beginning, it's pretty simple. It's just you, maybe a few friends. But what happens when that app explodes? What happens when you have 1 million users, or 100 million, or what seems impossible, 1 billion users? We're going to follow the story of a fictional app. We'll call it HappyBook, that faced exactly that challenge. And trust me, it's an incredible engineering journey.
So how do you even begin to think about building something for that kind of scale? Well, here's the surprising answer. You don't. You don't just sit down and design some perfect, unbreachable fortress from day one. It just doesn't work like that. It's really a journey of climbing one hill, feeling great about it, and then realizing there's a massive mountain waiting right behind it.
And this quote just nails it. When you're designing these massive, large-scale systems, every solution you come up with is not the finish line. It's actually the key that unlocks the door to the next problem, which is almost always trickier and more subtle than the last one. It's this constant cycle, and that's exactly what we're going to unpack today.
Okay, so our journey with HappyBook kicks off with its very first major growing pain. The app is getting slow, it's freezing up, and users, well, they're getting pretty frustrated. This is the first battle, the need for speed.
So here's the problem under the hood. The server, in its simple early design, is trying to do everything one thing at a time in a single line. So imagine one person starts uploading a huge photo, what engineers call a slow I/O or input-output operation. Well, guess what? Everyone else is now stuck in that line, just waiting. From a user's perspective, the app is frozen. The entire service grinds to a halt. It's a terrible experience.
So the first big fix is a powerful idea called concurrency. Now, this is a really clever trick. Instead of just sitting there totally blocked and waiting for that slow photo upload to finish, the server gets smart. It basically says, okay, well, that's chugging along. I'm going to switch my attention and go handle this other user's request to load their profile. It makes the whole system feel incredibly fast and responsive, even if it's still running on just one machine.
But of course, our elegant solution, concurrency, it has a dark side. By letting all these different threads of execution work at the same time, we've accidentally introduced a new, really subtle, and honestly very dangerous problem. Let's call it the peril of sharing.
And this is what we call a race condition. It is the classic textbook bug you run into with concurrency. You see, an operation that seems simple, like adding a like, isn't actually one single step for the computer. It's more like a 3-step dance. Read, modify, then write. So look at this flow here. Thread 1 reads the like count. It sees 100. But before it can write the new value, thread 2 swoops in and also reads the count, and it also sees 100. Now, thread 1 writes back 101. Then thread 2, working with its old stale data, also writes back 101. The right answer should be 102, right? But a like has just vanished into thin air. Your data is now officially corrupted.
So how on earth do we fix this mess? We use something called a mutex, which is just short for mutual exclusion. The best way to think about it is like a digital talking stick. Only the thread that's holding the stick is allowed to speak or modify the data. So to update the like count, a thread first has to grab this lock. This forces that whole read, modify, write dance to become what we call atomic. One single, indivisible operation. Nobody else can interrupt. And just like that, the race condition is solved. All right, so HappyBook is now way more responsive, and its data is safe from corruption. But it's getting so popular that it's just too big for one server. It's time to scale out, which means we now have to face all the challenges of the network. We've now broken HappyBook up into a bunch of smaller, specialized services. You've got one for user profiles, one for handling photos, maybe another for payments. But here's the thing. These services are all running on separate computers, maybe even in different racks in a data center. They have to talk to each other. So how do we make that communication simple and reliable when it has to cross a network?
Well, the answer for a long time has been the Remote Procedure Call, or RPC. And it is a beautiful, beautiful abstraction. For a software developer, calling a function that lives on a server halfway across the world looks and feels exactly the same as calling a function that's right there on the same machine. It magically hides all the messy, complicated network stuff. It's like magic.
But you probably guessed it. It's not actually magic. And that beautiful, simple abstraction, well, it's kind of a lie. Because the network itself is fundamentally unreliable. And sooner or later, that perfect illusion of simplicity is going to shatter.
This brings us to the concept of partial failure, and this is a core, fundamental challenge in distributed systems. When your RPC request times out, you are left completely in the dark. Did your message even get across the network? Did the server get it and then crash? Or maybe it did the work, but the reply got lost on its way back to you. You have absolutely no way of knowing which of these things happened, which leads to a really terrifying question. Should you try again?
And this is where a concept called idempotency becomes your absolute superpower. You have to design your operations so that it's safe to retry them over and over. I mean, think about charging a credit card. Retrying that is super dangerous. But what if you include a unique ID with every request? Then the server can see, oh, I've seen this ID before. This is just a retry, and it won't charge the card a second time. This is how you make an unsafe operation totally safe to repeat. Okay, at this point, HappyBook is a global phenomenon. We've got data centers in North America, Europe, Asia, you name it. But this, of course, introduces our next grand challenge. How do we possibly keep all of that data in sync across entire oceans? Look, those massive undersea cables that connect the continents, they can, and they absolutely do, fail. In system design, we call this a network partition. So when the European data center and the North American data center suddenly can't talk to each other, the entire system is forced to make a really, really difficult choice. The first thing you might want is consistency with a capital C. This means that everybody, everywhere in the world, sees the exact same data at the exact same time. A good analogy is your bank balance. It has to be perfectly consistent, right? It's the single source of truth for the entire system. The second thing you might want is availability with a capital A. This means the system is just always online. Every user can always read and write data. Now, that data might be a little stale, a little out of date, but the key is the site never shows them an error message. It's always available. And the third piece of this puzzle is partition tolerance. And this one is different. It's not really a choice. It's just accepting reality. The reality is that the network will fail. So for any real-world distributed system like ours, you must be tolerant to partitions. It's a law you have to design around. And this brings us to the famous crucial trade-off of the CAP theorem. When a network partition happens, and remember it will happen, you are forced to choose. You can have consistency or you can have availability, but you cannot have both. So for a social network like HappyBook, what's more important? Showing a user an error page or maybe letting them see a slightly out-of-dated like count? For them, keeping users engaged on the app is everything, so they choose to sacrifice perfect consistency to guarantee availability. And that decision leads us to our final and maybe most important philosophy. After solving all these nested, complex problems, you have a big realization. You can't just try to prevent failure. It's impossible. Instead, you have to expect it, and you have to design for it. You have to build a fortress. The absolute worst nightmare for any large-scale system is a cascading failure. Imagine a tiny, non-critical service. Let's say it's the one that resizes profile pictures. Imagine it fails. But other services depend on it, so they start failing. And then they take down the services that depend on them. And pretty soon, the whole system collapses like a row of dominoes. We prevent this with resilience patterns. A circuit breaker is just like the one in your house. It detects that a service is failing, and it trips, stopping all traffic from going to it, which gives it time to recover. And a bulkhead is an idea we borrow from shipbuilding. It's like the watertight compartments in a ship's hull. It isolates failures so that if one part of the system floods, it can't sink the entire ship. And that really brings us to the end of our journey. The goal, you see, isn't to build a perfect, unbreakable system. That's an impossible dream. The real goal is to build a resilient one. A system that acknowledges that failure is just inevitable, whether it's from bugs or hardware dying or network partitions, and is engineered from day one with the strength to withstand it and the intelligence to recover from it. That right there is the true art of building for a billion users.